All right, welcome folks. We're slowly getting the trickle in as you guys get the approve button to join the first of our Platinum sponsor webinar series for the Cold Spray Action Team of 2024. So we'll give everybody just a couple minutes here, maybe a minute or so to get signed in. So we'll just hang out here for a minute, but I do want to give you a bit of a plug for what's coming through the course of this year. So for those of you that are familiar with the Cold Spray Action Team, this is the premier gathering of cold spray scientists and engineers and users around the world. And as part of this, we have an annual meeting every year, June 11 to 13 this year in Worcester, Massachusetts. And we spend all the time that we can talking about how do we solve the hard problems in cold spray? How do we help kind of grow this whole industry, this whole ecosystem? And that's really the focus. And so as part of that, there's actually a Platinum sponsor webinar series, which this is the first of, thanks to SPEE3D and the team over there for supporting the organization. But the idea here is to give you guys a glimpse into what's going on, a little bit of teaser and excitement for what's going to happen at CSAT 2024. And really just an opportunity to learn more about what's going on in the cold spray community. Now, married up with this event is also the kind of sister event called the Large Scale Additive Action Team. So this is taking everything from cold spray additive, wire arc additive, friction stir additive, as well as some other techniques all about making really, really big parts, primarily metals focused. And obviously SPEE3D is actually a sponsor of both of these events because they do not only additive, not only cold spray additive, but also very large cold spray additive. And so I'm really excited to have the SPEE3D team here with us today. And we'll kind of walk through, make some quick introductions, and then we'll turn it over to them to really walk us through what's been going on in the last year, especially associated with some really cool materials development that I think is going to set the stage pretty nicely for CSAT 2024. And so if we want to do a quick round of intros, Steve, do you want to go first?
Yeah, hi everyone. Good morning and good afternoon. Stephen Camilleri coming in from Darwin in Australia. I'm the CTO and co-founder of SPEE3D.
Awesome. Andrew, how about you?
Hi, everybody. So I'm Andrew Duguid. I'm SPEED Senior Metallurgist. As the blurb says, I've sort of come to it by a circuitous route, but there's a bit of powder metallurgy in there and a bit of foundry experience. And I'm in Brisbane at the moment, which is warm and humid. And thanks everybody for coming.
Awesome. And Pierre?
Hi, I'm Pierre Devaux. I'm responsible for our educational customers at SPEE3D. That means not only on the sales side, but also on finding partners that are going to be helping us. And we'll talk a little bit more about that a little later in the presentation.
I love it. And I have to say, you guys look so good in these pictures. So kudos to the marketing team for making that happen. So that doesn't really get you any brownie points with the community, but everything that you're going to talk about here, I think is. So with that, I want to turn it over to you guys and blow our minds with all the great things you guys are doing in the world of cold spray additive.
Right. So a little bit of background on SPEE3D. So as Aaron introduced, we're a company that makes cold spray additive equipment. The company's been around since about 2016. And really we focus on being able to make metal parts very, very quickly. And indeed, we've been doing a lot of work with various defense forces doing that in the field as well. So I might throw to the next slide. And I'll yield to Pierre.
Thanks, Stephen. So part of this presentation today certainly couldn't have been done without our research partners. So some are on the academic side and some are on the commercial side. But we do things quite differently at SPEE3D. With our technology, it's very much an open system. So you have the ability to really broaden the range of materials that you're able to work with and you're able to research, really. So with that increase in the material portfolio comes an exponential increase with the number of different applications and alloys that we can take a look at. And we can't do all of those things internally at SPEE3D. We don't have the capacity. We're very focused on, building machines. So we do have this open system. We're looking for research partners. You'll see some very interesting things today. And afterwards, if you need to talk to somebody about, what we can do, how we can partner, how we can work together, that's going to be me. So I'll be happy to do that. And again, that opens up a whole bunch of different applications for you. So different alloys, material properties, research, coatings, morphology, shape of parts, post-processing, all of those things. I'd be happy to speak with you about that.
Right. So today the subject is nickel aluminium bronze, or I believe in the US it's called nickel aluminum bronze. So this is a material that it's pretty well known. It's very common in a maritime sense. It's quite strong. It's very good at wear. It's self-lubricating. It's good for erosion, but particularly good for corrosion in seawater. So it's got the high copper content in the alloy, which makes it antimicrobial and anti-fouling. It prevents sea life from growing readily on the surface and damaging the surface. So it's a very valuable material. And there's a collection of AI images there, which are all, royalty-free of the different parts. So those of you who are familiar with those parts can look for the small details the AI got wrong. All right, next slide. So nickel aluminium bronze is not just any bronze. So this is a bit of a info point for the non-metallurgists in the crowd. So on the left, we have a thing called the head of Sargon. It's about 4,500 years old, as far as we know. Nobody really remembers, but it's made of a bronze, which is a 90% copper, 10% tin. This is a fairly common alloy from the time. You can see it's survived remarkably well. Really, it's quite well preserved. So bronze is a remarkable material for lifetime, especially when it comes to corrosion. On the right, you can see a ship's propeller made from nickel aluminium bronze. So these are not the same material, despite both being called bronze. Just like steel, there are many types of steel that behave very differently. There are many types of bronze that behave very differently. So in particular, the nickel and the aluminium are not ancient materials. They're modern materials that were isolated fairly recently. So that's a completely different material. And I just want to make that clear that we're not talking about the image on the left today. We're talking about the image on the right. Okay, next slide. So let's talk a little bit about our process at SPEE3D. So we use cold spray to do AM. And AM is really about getting the geometry right, the shape, and about getting the material right, the material properties right. So we use our printer to get the geometry right. That's what generates our part shape. The material gets sprayed together, and we end up with a dense metal part that in which we can improve the internal bonding. So we use a furnace, a heat treatment of some sort, to improve the material properties post print. So you can see in that second cook stage there, the part from the printer goes in, and comes out in a much better metallurgical condition. And on the right, we have the cut process. So this is where we take the object that was printed by the printer and then heat treated, and then we make the final dimensions, the final parts of the shape, precisely correct. So this is our normal process. Next slide, please. So how do we go about developing a new material for our manufacturing process? So, where's the work? Where's the effort? So we just wanted to make a few points today to describe what we normally do. So, where's the work? So we start with the feedstock powder or powders. So, this is often an iterative process. You try something and then later on you try something else once you've determined it needs to be different. We have to work on the best way to spray it. So most of the cold spray community will understand this part very well. It's all about temperature and pressure and, the tool pathing properties. The resulting material is then heat treated. We have to determine the best way to do that. Heat treatment is a very a very open process. There are lots of different ways to do it, particularly navigating time and temperature. Then we test the material and we determine where there are opportunities for improvement, and we go again. And this iterative process, going through again and again, is how we develop a cold spray material. Once we're at the point where the material performs as we would like, and we've determined that we can generate the material properties required to a minimum level over and over again, we establish our quality controls, we write our operating procedures and our quality processes, and then we generate a data sheet that provides a minimum performance level. So this is a little bit unusual in the AM world, is the idea that we're promising a minimum performance level from the material. So most of AM, has a kind of suck it and see approach when it comes to material properties. But indeed, if it's a manufacturing process, people need to be able to use it. To be able to use it, they've got to know the material is going to work. So this is our normal process. So I'll throw over to Andrew for the next slide.
Yeah, hi everyone. So what I'll talk about here is just sort of the front end of the process, the development process that Steve's just described. So really we've sort of said that initial sort of development cascade. And I've sort of, in the graphic you see there, sort of the first thing we think about is like kind of where are we going to get powder from and what that powder is going to be like. We start out with a theory of the material that, that includes all of those elements that Steve describes there. We think through all of those issues, but we go, okay, well, let's start with the powder. And the next step, obviously, is to work out how to get that to deposit and then to hit the composition of the alloy that we're targeting. And that's a non-trivial step for reasons that we'll address in a moment. Having done that, we move into kind of like the heat treatment phase where we're looking at processes like homogenization and bond formation. And then the next step beyond that is kind of hardening, because we have, for any structural material, we have a strong preference for materials that have like a thermal hardening mechanism. And the reason for that will become clear in a moment. And at the end of all of that, you've got something that kind of looks like an alloy, and then you do your tensile testing, as Steve said, and then we look at that stuff very closely. We look at micros, we look at fractography, and we decide what we don't like about what's going on and how we're going to amend that. And then we go through that process of iteration. So next slide, please. Okay, so powder acquisition is a non-trivial step for us, and indeed the whole theory of our alloys are complicated because of this basic thing. So we've got a slide here that basically talks about why it's hard to cold spray highly alloyed materials as a general rule. And so we start out with a little bit of theory sort of thing. And so the metallurgists in the room will be familiar with like kind of alloy segregation or Scheil solidification. That's what we're seeing in these images here. So we've got a 7075 particle that's been gas atomized. And what we can see is that the alloy elements are really sort of mal-distributed kind of throughout that alloy. They're all present on the grain boundaries. No doubt they've formed all sorts of odd intermetallics. It's possible there's been some inadvertent hardening. The thermal hardening mechanism has actually operated inadvertently throughout the kind of production of that powder. And what that means is that we're left with a powder that's not actually particularly sympathetic to being sprayed. It's not to say that you can't do it. Obviously, people do it all the time, but you have to go to a higher degree of effort to do that, to sort of overcome those sorts of problems. And indeed, another whole other avenue that people explore in this is in terms of resolutionizing those particles and kind of rendering them into a softer state. Also, kind of a good way of solving the problem. But we take a slightly different approach to that, by and large, and so we might move on to the next slide. Yeah, so here's kind of, I guess, what I just said, really, kind of like, it's difficult to spray highly alloyed powders. It's not impossible, but it does make life a bit harder. And, kind of as a loose generalization, obviously, the higher the alloy content and the more aggressive the hardening mechanisms, the greater the kind of the difficulty that you get with that. The powder's harder, it's more difficult to spray. So what that means is that you're bucking all of those other things, kind of like higher expense in terms of, kind of getting greater nozzle energies or living with poorer deposition efficiencies, kind of lower build rates, And a critical one for us is kind of, what you're left with in terms of porosity and residual defects. So obviously NAB is kind of quite a rich alloy, like its alloy content is about 20% and it's quite hardenable. So, for us, it's quite desirable to find another way around that. And kind of graphic on the right there is actually, we were lucky to find a bit of work done on the deposition efficiency of cold sprayed NAB with heat treatments. And you can see that the heat treatments can make a big difference. You guys have gone up from kind of about 8% to as much as 20% there. So heat treatment can be an effective route depending on the alloy, but we might go on to the next slide. Okay, so our observation right from the start, kind of almost inadvertently, is that sort of everybody starts out cold spraying elemental powders because elemental powders are soft and easy to spray. And so, we've developed a methodology where we look at either spraying blends of elemental powders or spraying combinations of master alloys. So we take the basic alloy and break it down into more cold sprayable kind of components. And that might be splitting the alloying elements into two major groups and spraying kind of a blend of two powders that each have some of the alloy constituents in them. Or it might be actually breaking the alloy down completely and just spraying a blend of elemental powders. And what we can see here is the results of our trial for nickel aluminium bronze. And so there's two kind of data sets there. The orange one is one where we had a combination of some elemental powders and a CuAl10 master alloy. And we were at that stage playing around with different blend aluminium contents because we were dialing in our composition. And you can see that the DE for that master alloy blend is a fairly stubborn 40%. Now, unfortunately for us, that's about the limit of feature formation in kind of our AM process. So if you're below 40%, you really can't form the features on the part particularly well. So that wasn't particularly attractive. And happily, what we found is that when you sprayed the elemental blend, we got a pretty substantial increase in deposition efficiency. Has a slight, kind of trend with the aluminium content and then sort of seems to plateau out from about 9.5% on. So that's that first stage. We selected our powders and we worked out how to get deposition. And then obviously you can imagine doing this sort of sweep across the aluminium content. What we're doing there is dialing in the aluminium content of the blend so that we wind up with the right amount of aluminium in the alloy at the end. And what this told us was we were way better off just sticking with an elemental blend. Okay, so we go on to the next slide. Okay, so what does that look like? So as a process, you can sort of see it mapped out there. We start out with elemental powders is what we landed on. We blend those, we cold spray them. We do some heat treatments, winding up with a hardened kind of alloy at the end of that. And the critical thing to look at here is this homogenization process. So if you look at the micro on the left there, that's our as sprayed material. And as you would expect, you can literally discern each of the different alloy constituents as elemental powders in that microstructure. So that's what that looks like. We're pretty happy with that. Anybody who comes from a presence into powder metallurgy background would be overjoyed to see that. It's got almost no porosity and there's intimate metal contact, those two very difficult things to achieve in classic powder metallurgy. And the question is, but that's not an alloy, that's a physical mixture. So what do we have to do with that? Well, we heat treat it, and we heat treat it, reasonably aggressively. But what we wind up with is something like what you see on the right-hand side there. So you can see that all of the individual particles have lost their identity, and you're seeing a more or less homogeneous matrix, with the classic nickel aluminium bronze. There's some, high temperature kappa phase there precipitated out on the grain boundaries. And there's a few bits of pores there, probably Kirkendall porosity for, again, the metallurgists in the audience, porosity that you get when one thing dissolves into another thing. And we'll talk a little bit more about that kind of going forwards. But that's basically what we're seeing there. If this was the first time that we've done an alloy, we go, that's fantastic. We've achieved homogenization. Microstructure looks pretty well resolved. And, maybe we've got a little bit of problem with porosity. We'll have a think about that. And you can see the heat treatment sort of on the right there. Okay, so we go on to the next slide. Okay, so here is where we started to really dig into kind of developing the alloy and starting to tune the alloy constituents. So we were, and again, this is why we'd start to look at what are we getting and what do we need to adjust. So 11% aluminium blend we've got a fairly sort of homogeneous microstructure there that's all kind of like primary alpha with a little bit of decomposed beta phase in it, where you can see the kind of scrubby bits that'll be kind of decomposed beta. So it's a little bit higher and precipitates. The 12.5% blend obviously is sort of mostly kind of like decomposed beta phase, sort of beta prime or decomposed beta once you've aged it. There's obviously a little bit of fine kind of alpha phase, and then you can't actually see it there, but there's actually quite a lot of fairly coarse kappa phase distributed throughout that microstructure there. It's not very clear there, and we go, okay, we don't like seeing an awful lot of intermetallic, you know, kind of in a microstructure, so that might tend to push us back towards the 11% kind of blend. So if we'd like to move on to the next slide. Okay, so the next step is to look at, can we get the thing to harden? And that, in a lot of ways, that's the acid test for have you really homogenized the alloy successfully? Because obviously it's not going to behave itself through the hardening process if all of the elements are not participating in that reaction. And often we do have the thing where we convince ourselves that we've succeeded, and then the hardening doesn't quite go the way that we want, and we realize that we have to work a bit harder on homogenization. But these are the results we got kind of after a little bit of work in NAB. You know, that's more or less what we expect, right, from the kind of published data on this alloy. You know, that's great. We've achieved a hardening reaction. We can kind of now dial in the strength of the alloy, where, you know, kind of where we need it, based on obviously modifying the kind of like the aging kind of treatments. And as I say there, the kind of iron and the nickel, you know, must be participating in that reaction. Otherwise, it wouldn't be hardening in that way. Okay, we move on to the next slide. So this is the exciting bit for me. This is like kind of, this is what I hang out for. And this is some tensile results kind of based on that early stage kind of work with a few different aluminium contents. So I'll sort of talk through, you know, this plot. So what we do to visualize our tensile data is that we take the yield and UTS values from a set of tensile tests. Typically we do between 3 and 5, mostly 5. And we average those, we get an average yield and an average UTS. And we plot both of those figures against the strain to failure, which is, so that's what you can see on the two axes there, is kind of strain to failure and the yield and UTS. And what that allows us to visualize is kind of, you know, how ductile the alloy is, and independent of that, kind of how hard it is in terms of its yield strength. And there's actually quite a lot that you can infer from a plot like this, if you sort of sit down and think about what might be driving trends and so forth. And we do an awful lot of this at Speed. So what I've done is I've just put one of the wrought specifications on there for nickel aluminium bronze. That's the CW308G spec. And that's actually pretty good. That's for a material that kind of we are using a conventional heat treatment, for want of a better term, just a conventional homogenize and sinter and an aging treatment. We've got something with a bit of a knockdown on wrought, but in the ballpark at 11%. Now you can see that the 9.9 kind of data point is not so crash hot, and the 12.5 is really a bit awful. Well, it's quite strong, but it's terribly brittle. So what would we say about that? Well, we actually rely on the aluminium to do some sintering for us in the heat treatment because it liquefies. You can imagine that as we heat the alloy up quite quickly and the aluminium goes above its melting temperature and liquefies, and it helps us to bond together any of the unbonded surface and resolve the porosity. Now, our kind of guess, not that we've done the science on this sort of thing, but if I had to guess, I'd say that the 11% is working a bit better because it's actually sintering a bit better. And that's actually pushed the data point out, if you look at it, sort of in a northeasterly direction. So it's both got more elongation and higher strength. And really the only way that you can do that is by improving either reducing the defect size or improving the fracture toughness. So that's probably a sintering thing. That's why we say that. You know, would I bet a sheep station on it? You know, maybe not, but that's probably what's going on. The 12.5%, by contrast, we would have liked to think it would have sintered even better, but it's really bad. Why is that? Well, we think it's probably because we've got too much kind of coarse kappa precipitate in it, and that's obviously causing the, you know, kind of the fracture toughness to collapse, and therefore we're getting a kind of a brittle failure rather than a ductile failure. So anyway, that's a good place to land in terms of a proof of concept. We're pretty happy with that. So we might go on to the next slide. So this is with a little bit more kind of optimization, looking at that 11% blend. So we've got the previous data point there, and a second data point that we did with a slightly different heat treatment. And what I've done there is I've added in the sort of the 958 sand cast specification there. So how do you gloss that? Well, the first thing is that, you know, kind of users have maybe got a choice about like kind of what they would prefer. You can have an alloy that's, you know, moderately strong at 330 MPa. You know, not an awful lot of ductility, but there might be applications where you'd want to use it that way. Or you can go a little bit on the safer side and knock the yield stress down a bit, get a bit more elongation. And you're looking at an alloy that's got a yield stress that's comparable to the sandcast, or maybe a little bit above the sandcast value, not quite as ductile, but still, you know, kind of, you know, enough ductility to be a serviceable sort of engineering material. So that's really great. With, you know, that's good place to land. There's more work to do, but we're pretty happy with that. And you know, we can see users for that material. But we might go on to the next slide. Okay, the question that then arises is, are there other users out there who might want to use a higher performance alloy and are prepared to pay a bit of a premium for that? And an obvious next step for anybody who's got sort of any, you know, kind of background in casting or powder metallurgy is to look at hipping. What happens if we add hipping into that process? Now, obviously, the pressure from the hip is going to aid the sintering process enormously, as well as kind of collapsing some porosity. And that shouldn't be too controversial. One of the questions that pops up, though, is when do you do the hip? So we have a choice that we could cold spray things, homogenize them as we have just seen ourselves do, and then run them through the hip. Or we could hip the material first and then conduct all of the heat treatments, you know, kind of after the hipping process once we've resolved all the defects. It was a hard call, and so we decided that we'd check both of those, and turned out that it was well that we did so. So if we go on to the next slide. Right, so what we see here is the microstructural outcome of each of those two production sequences. And the one on the left, you know, makes us pretty happy. It's a pretty resolved microstructure. It's got good homogeneity. Some of the grain boundaries look like a little bit odd, but it's definitely something that we'd take to a tensile test and see how we go. The one on the right looks absolutely horrible. I'm sure everyone would agree. It's full of porosity. So this is the dreaded Kirkendall porosity that we alluded to before. So what we're seeing there is that we've done the hip process, and it would seem like we've got a fairly good degree of bonding kind of in the material as a result of the hip. The microstructure, obviously, you know, key point here, right, looks nothing like a cold spray microstructure anymore. So that's all well and good. But what we realized after we dug into it is that the hip cycle is nowhere near long enough or aggressive enough to completely homogenize the aluminium and the iron and the nickel, for that matter, or the iron particularly. And what that means is that the homogenized step is still homogenizing the alloy kind of after it's otherwise been formed. And the problem with that then is that the aluminium is like gradually diffusing away kind of into the matrix. There's no longer the potential to generate kind of any liquid phase. And instead what you wind up with is kind of these voids where the aluminium rich areas, you know, used to be. And there's nothing that in that sequence that's going to do anything about those voids. And so, you know, obviously we conclude from that the sequence on the left is the one that we want to proceed with, and that's what we did. So yeah, if we can go on to the next slide. So here's the punchlines of things. So basically what we're looking at here is another one of those plots, with the yield and the UTS plotted above one another on you know, in the Y, and then the strain to failure sort of locating both those points on the X-axis. And this is pretty much our entire data set for a whole battery of tests that we did, you know, predominantly for different heat treatment conditions, different solutionized and different age kind of procedures. And obviously what that's doing is just driving the hardness of the material to different values. And, you know, any metallurgist will sort of recognize that sort of, it doesn't really have a name. I just call it a metallurgical trend, where you're trading off hardness against elongation, you know, and you're getting that sort of kind of that southeast sort of gentle trend there. So this was, you know, a fantastic result for us, and sort of really, you know, frankly, above expectations, really. So you see the square red dot there is the yield stress value for the C958 sand casting specification, and the green square above that is the UTS requirement. And we're basically meeting those requirements pretty comfortably. We've got a sort of a margin on whichever way you want to look at it. We've either got a margin on strength or a really pretty significant margin on elongation over the sand cast spec. But that's a fantastic outcome for us, and we're really happy about that. What we didn't look for is that sort of when we inadvertently, moved the conditions up to a higher hardness value, we're actually not looking too bad against the Rort spec either. It's sort of a little bit touch and go. But we do a statistical study on that. We'd find that we were, basically meeting the Rort spec as well with that hipping process, and that's great. That's sort of a holy grail. Metallurgists are pessimists, right? So I run around telling people, kind of, no, we are not going to meet the Rort spec. And it's always lovely being proved wrong, kind of when we do it anyway. Okay, so we'll go on to the next slide. Yeah, so summary. I think I was going to do the summary, so I'll just sort of punch through it. So basically, what are the takeaways from all of this? So spraying elemental blends and then applying kind of like classic powder metallurgy heat treatments to them is a valid way to make high performance alloys using cold spray. It is, a route to getting a good outcome. It's by no means the only route, and it's not the only thing that we think of, but it is one that's worked pretty well for us in a bunch of cases. Kind of cold spray additive manufacturing is a viable way to make maritime parts that might otherwise have been cast, and you can see a fantastic kind of case study just there. Classic kind of cast part done out of cold spray and machined up. Hipping obviously is a really useful addition, particularly to cuprous alloys, but you have to work out how to use it because there's other things going on, and you have to kind of synthesize all of that. And really the punchline is that we're basically finalizing kind of two variants of that material, kind of an unhipped and a hipped. And we will be kind of like updating this group kind of in June on our progress on that. So that's me. I think we can go to the next slide. So Pierre, I think this is you.
It is. I was just unmuting myself. So just to summarize, again, I talked a little bit about academic research. And one of the reasons I did that, there's a lot of researchers from academic institutions on today's call. So I wanted to speak to them. But again, I wanted to rehash this idea that we do academic research differently with our partners. We're not just looking to sell machines, but we're actually looking to form partnerships with our customers so that we can work together. And this particular presentation from Andrew and Stephen, it couldn't have come together without a couple of our partners. So they are very important to us. They do a lot of collaborative work with us. And again, we can't do it all. So we have a tremendous number of projects that we'd like to take on, but we don't have the bandwidth to do it. And we're looking for academic researchers to partner with us on that very process. So the good news, next slide, is that there's a lot of funding out there in the world. Global stats, again, worldwide, $497 billion annually being spent on academic research. The compounded annual growth rate of over 8% through the next 4 years. So it's a great situation to be in, right? Governments around the world are funding research, and they're putting their money where their mouth is, really, and funding it at a higher rate than they do other projects. So big initiatives, Industry 4.0 and sustainability in Europe. That's the angle that if you are in Europe, that's the angle that you should use when you're writing grant proposals. In the US, we have a slightly different focus. There is the National Science Foundation. They're funding about $9.8 billion in 2023. That's an increase of 12% versus 2022. The the proposed spending in 2024 is 11.3 billion. So a big jump in funding from the NSF, and DoD seems to have a lot of money as well. They spend a lot of money on research, development, testing, and I forget what the E stands for, but 123 billion in 2022. 2.8 billion of that is spent on basic research. 50% of the basic research budget, 1.4 billion, is spent with universities in the United States. So the big programs there are Office of Naval Research and the Army Research Lab through the DURP and Murray grant proposals, grant programs. So they're great ways to get some funding for your research, especially if you are looking to focus on, marine or naval applications here. ONR is the way to go. If you're looking more about, creating, new materials and parts that can be deployed in the field, then the Army Research Lab is a great funding source as well. So I wanted to wrap it up with that. Stephen might have a few words to say at the end. That's it for me. So if you have any questions, please come to me about partnership opportunities. Be happy to speak with you.
And I just wanted to say thanks in particular to Solvus Global and Penn State for their support through this program. It's been wonderful working with you guys.
We agree. So this was awesome. So we have plenty of time for Q&A, and I know we've got some firing in the background, and we've got some that are answered and in progress of being answered. But we'll go ahead and we'll cover a couple of these live so that everybody can kind of hear the responses and maybe dive a little bit deeper if we need to. But awesome job, guys. Really love seeing the balance of the technical and the academic kind of coming together here and actually sharing knowledge with the community, because that's ultimately what the Action Team series and CSAT and LSAT especially are all about, is creating that knowledge that can be shared so that the whole ecosystem grows, right? So love seeing that be shared with the community. There's a lot of the questions around here that we're kind of answering as we go is just diving back to that idea of the elemental versus the pre-alloyed. And maybe you can talk a little bit about just a little bit more about the framework of when you feel like that works, the elemental, and when you feel like it doesn't, and when you feel like the alloyed works and when you feel like the alloyed doesn't.
Wow, okay, that's a great question. I suppose my department. I guess what I'd say is that I would prefer to spray fully alloyed powders every day of the week at one level, because then I would not have to worry about how to homogenize them. And so that's one part of that answer. There's not a simple answer. I'm legendary in speed every time. But there's a saying that there's a single answer to every metallurgical question that's always right, and the answer is it depends. So that's the answer I'm going to give here now. It depends. So at one level, I'd prefer to spray an alloyed powder like any time, because then I don't have to worry about homogenization. And indeed, that's what we do with our 6061, because the 6061 is pretty soft as an alloy powder. So that's the first part of the answer. The next part of the answer is, if for whatever reason, I'm worried about the material not bonding particularly well, so maybe it deposits, but it's not bonding as well as we'd like. What I'm going to do then is to look at ways that we can sinter that alloy, in order to make up whatever that deficit is, whatever those residual defects are. We need to get them out by sintering. And so I'm going to look at that, and I'm going to ask myself the question: does this alloy sinter well as a fully alloyed powder, or does it sinter? Does it have a preference for sintering, again, classic powder metallurgy terms, by having a blend of powders that might make a low temperature liquid? And again, that's a case by case basis. The 6061 sinters not too badly, as an alloy powder. Other materials that we've worked with, like 316 stainless, actually sinter fantastically. They're not exactly easy to deposit, but their sintering performance is great. So in that instance, again, we'll stick with kind of a fully alloyed powder and just go, well, the sintering performance is what we need it to be, and we'll stick at that. It's heaps simpler. With the aluminium bronze, we found that, we got very poor deposition behavior for a range of different, as you saw, kind of like fully, more or less alloyed conditions. And in addition to that, it's not a particularly favorable sintering alloy, particularly, it's got a very, very narrow freezing range is one of the problems, which means it's very touch and go, taking the thing up to a high temperature and then getting it to weld itself together. So for us, in that context, it works better on every level to be blending, for instance, the copper and the aluminium together, knowing that, when we heat that up, we get a transient liquid, formed, first by the interalloying of the copper and the aluminium. So compositional melting for anybody who knows sort of powder metallurgy. And then just from the rest of the alloy, the aluminium just like dead set melting because the temperature is rising so quickly. And that works fantastically for us. So sort of a case by case basis, I don't want to give the impression that I delight in complex alloy kind of design. It's something that we'd prefer to not do if we could not do it. But there are some situations where it just winds up being the right answer.
Yeah, sometimes the KISS principle just doesn't quite work out the way you want it to.
Yeah,
as long
exactly.
as you understand it, it gets you the right direction.
Yeah, that's right.
So
yeah.
Some of the other questions here that I think maybe follow a similar set of it depends answers. So I'm going to take that one from you, Andrew and Steve, and not give you that answer. But some of the questions that we're seeing popping through are really about the powder feeding and maybe the theory of powder blending and powder feeding and maybe why you do it before you get into the feeder, or maybe it makes sense in the future to do blending as part of the feeders, and kind of what your thought processes are there behind the right approach to blending.
Right. Okay. Yeah. Okay. I'm struggling to not spit out it depends. Maybe I'll go instead for the keep it simple kind of principle, the KISS principle. Yeah. So historically we've started often with elemental blends and offline blending. And the reason for doing that was that it was simply it was sort of the lowest barrier to entry, I guess, to doing any of this stuff. It meant that we could buy powders off the shelf pretty much and combine them in ways that sort of pleased us. Kind of blending is not, something obviously that has to be done carefully because there's some safety concerns, but it's not a difficult thing to do. So we did all of that, and it just meant that it gave us a very broad scope of agency without too much kind of complexity in terms of the whole process. Obviously, going forwards, we'd love, and we are intending to get to a point where we're sort of, for instance, fielding, multiple, powder feed lines, and we can actually dial up compositions. That would be fantastic. I would love that. But that's sort of like a next gen kind of a step. So at the moment, it's a kind of it's a supply chain solution, and that seems to be working pretty well for us. Is that? Excellent. I think that's a complete answer to the question. I don't know if I missed anything there.
I think it gets us there. Thank you. I want to go to maybe the other kind of side of the spectrum here. Pierre, we talked a bit about the academic community and how they can get engaged with the ecosystem here. And I'm just curious if you want to talk a little bit about, or maybe kind of offer some guidance to the folks who are doing research in that world about the best mechanisms to partner with you guys, and thinking in particular about how do you walk through and really right size a machine for those research partners based on some of the different criteria that you were talking about.
Yeah, that's a very good question, and it's very dependent upon what those researchers can bring to the table, right? Like, we can bring equipment to the table, we can bring some level of expertise, we can bring some work that we can do at SPEE3D, but if there's a good fit for what the researchers are looking to do and what we're looking to do, then we have a very good possibility for partnership. If they're doing something that's very groundbreaking, but really has not a good fit for what we need to do for our objectives, then it's not going to work very well, right? So it really depends. It's a case-by-case basis. It's something that I have to get involved with, and Stephen and Byron and Andrew, and we have to have a discussion in terms of what they would like to do and whether that fits with us.
Okay. And do you find most of the time with the university teams, does it make sense to go for you know, the big X-speed printers, or go down in the field, you find most of the time it's more on the light speed side. Where do you think is kind of the right machine for the right tool for the job, as it were?
Another "it depends" answer. So it depends on the right.
It's not just metallurgists.
It's not. No, it depends on what they're interested in doing. Again, if they're looking at material development and they're just looking at building, you know, spraying little penthol bars and coupons, and then a small machine is fine, right? If instead you're looking at collaborating with industry and building some of the biggest parts that you can get, you know, then yes, then a warp speed is the way to go. Now, I will say that of all the schools that are speaking with us right now, the majority seem to go for a warp speed. So they really like the extra large size, you know, for the build platform. So yeah, it's surprising to me actually, but warp speed seems to be winning that competition.
Maybe it's in the name. I tease. So you started talking about part size, and I think that's a really important segue into just understanding what is the scope of what you guys can do. So walk us through biggest, baddest part that you guys have produced, and what's the story behind it.
I can take that one if you like. So yeah, it's a good question. So I mean, why do we even do what we're doing? I guess that's the fundamental question. Why are we even doing this? Like, this is hard. Why are we trying to do it? And the answer is metal parts are difficult. Manufacturing metal parts is difficult by, you know, any means. We've got processes that have been around for tens of thousands of years, but you know, nevertheless, people still have difficulty getting the metal parts that they need. So, you know, people quote additive manufacturing as being the ambulance at the bottom of the cliff. Once you've tried everything else, you know, you call the additive guys and see if they'll help. So we find ourselves in that position as well. And it all comes down to the parts being difficult to get because of some issue, complexity or cost or time, and people wanting an alternative. So large metal parts are, you know, orders of magnitude more difficult to get than small metal parts. There are so many different issues around the fabrication of large metal parts that it seems like, you know, additive is a perfect fit for large metal parts, because there really are no good ways to make large metal parts currently. So if additive can rescue that particular cliff diver from the beach, then, you know, that's going to be huge. So we're doing work in that space. The warp speed machine is the machine that you know, currently will build the largest parts, up to about 45 kilograms if we really push it. And I mean, there was a part about that size that we made. I think it was for a trial called ITX, and people can find the media on that. We made a very large, you know, aluminum alloy foot, which supported 20 odd tons of armored vehicle successfully the first time it was tried. Which, you know, was a little nerve-wracking, I'll happily admit. But, you know, this part needed 2 people to carry it around. It was a big part. It was right up there. And especially in aluminum, you know, aluminum parts, you know, a big aluminum part that's also too heavy to carry, like that's a big part. So we were able to make that overnight in a car park, you know, versus over however long at a foundry. So I think large parts, everyone's got an appetite for AM to go after that. And so, you know, we want to be able to present some good results at LSAT later this year on where we're up to with large parts.
And do you guys, are you going bigger, or do you think 45 kilograms is the limit?
Well, I think as we announced last year at LSAT, we are trying to go bigger. So let's try and get to tons.
I love it. I love it.
Parts. Yeah.
So kind of scaling with that then. So we've got the big parts, and classically, as we've kind of talked about before, those typically have been cast or forged in a variety of different manners. Maybe they've been had some sort of powder metallurgy process, but we're really talking about the big scale processes at this point. And there's always unique property requirements for those. And so as you're getting into this, what are you seeing for property matching? Where do you think there's success? Where do you think there's challenges that remain to be solved that maybe some of those academic partners that we talked about can start diving into?
Well, where do you start with this one? I would say there's a huge amount of standard materials that are yet to be deployed well by AM processes. So that would otherwise be standard. So, looking at your high strength precipitation hardening stuff, barraging steels, titanium alloys, your incredibly oxide resistant nickel alloys, all of those classes really, additive manufacturing is still kind of trying to come for those complex materials. But one of the questions I keep asking, usually our university partners is, why are we not looking at the advantages of the AM processes as ways to generate new materials? So that's a hugely wide open question with a lot of opportunity behind it. If people want me to talk about that, I can talk about that all day. There's so many opportunities out there. Andrew,
give us one, Steve. Give us one of your favorite opportunities.
Favorite opportunities.
Maybe I'll jump in here. So
Yeah.
One that's obviously a big one in everybody's mind is titanium. There's a lot of noise and a lot of interest, I guess, around that material. Our preliminary gloss on that obviously is you have to manage the safety risks with that. Throwing it around in the cold spray process is something you need to think about, but it's obviously that's a manageable thing. You just have to manage it. And that's one that there are other things about titanium that make it pretty amenable to our process. And certainly at the particular take on it that we have, our expectation is that it will actually sinter really quite well. It's a little bit hard to pin down the generalizations. We're looking for alloys that can be rendered into a soft condition as a powder by whatever means. Now, does that mean maybe heat treating them to solutionize elements? Does it mean breaking them up into elemental blends? Does it mean breaking them up into master alloys? That's a total case-by-case basis. So it really is, metallurgy, I'm sure the metallurgists out there would agree, it's mostly a pretty conservative art, and it should be really. And this is by far the most exciting metallurgy that I've ever done, because it is an open-ended problem-solving kind of exercise. You start with a standard alloy and you start thinking about how you can either tweak that in terms of composition, or how you can break it up, or how you can treat the powder or whatever else in order to lead to the outcome. You want a fully bonded part at the end of that, with a hardening mechanism that's operating. So I think, titanium would be a good kind of plug for me at the moment. There's a bunch of stuff in the sort of marine grade cuprous field that we could split off. There's avenues to look at in terms of aluminium. We're sort of moving more towards an aluminium PM kind of approach. Some work in ferrous, which I'll probably be a little bit mum about at this stage, because we're working on that kind of internally, and I won't say too much, but that's certainly an opportunity if people are very keen.
So the sky is the limit, is what we're saying.
Yeah, I mean, I guess the generalization is, as you start to throw harder phase materials in there, it gets challenging, but then there's ways of doing that as well. I mean, we're really looking for partners at the moment in the to your point, the whole of Solvus, we're looking at people who can engineer powders, because that's an avenue that we haven't really dipped our toe into yet, and that's something that that we're going to be working kind of with you guys sort of further on. Is engineers.
Always excited to do so.
Yeah. No, it's fantastic. So that's it, right? Sort of that's where we haven't gone, except on one brief occasion, and it's very fruitful. So why haven't we pushed on that lever more? So we'd love to get into that space as well.
Love it. How about, so we talked about some of the future looking materials, and for the folks who are on the line here, the Q&A is still buzzing, so please feel free to use it. We've got time for a couple more questions here. But one of the ones that kind of keeps popping up is around, materials that we kind of know and understand that really push the limits that we're excited about. So thinking about maybe examples in like nickel or even maybe cobalt super alloys that you guys have good kind of use cases and evidence for, the stellites, the Inconels. What are kind of some of your favorites there? Maybe some good examples of how you've been able to use and demonstrate those materials.
Again, maybe I'll take this one. There's probably one good solid generalization in that space, obviously, is that, people use powder processes where they have kind of miscibility gaps. So when you can't form the alloy successfully from the melt and then through some sort of, kind of like solid processing route. So you think about maybe kind of very highly alloyed cold steels are one example of that. Another example might be high temperature, high conductivity copper alloys, which are not, there's a few of those that are quite difficult to make by conventional routes, and they lend themselves to powder production, but then you've got to consolidate the powder. So that'd be one kind of good example. Anything that you can't kind of jam together by other processes, and then because of that lands in the powder metallurgy space. Yeah, any of those specialty alloys. Yeah.
Okay, fabulous. And we're getting close on time, so I've one last question that comes only because I know I need to send some of my team to Australia in a couple of weeks. And I recall back to my high school days when one of my teachers went to Australia and brought back Tam-Tams and Vegemite. Tam-Tams were good. The Vegemite I couldn't quite handle. So when my team comes to say hello, exactly how much Vegemite are we going to have to deal with?
We did recently have a global event here, and we did encourage our US team to give it a try. So yeah, anyone who's curious about Vegemite in the US, my advice would be to check YouTube for Hugh Jackman's public service announcement describing how to eat Vegemite. It's basically salt, so don't stick a spoon in it, eat it like jelly. It's not the same thing. Yeah, lots of butter, good quality bread, and like a little fingernail's worth of Vegemite spread over the bread. That's the way to do it.
Yeah, the whole spoonful is what got me as a kid. That was a
Yeah. Yeah, that's sort of like that aversive kind of like kind of experience that people have, and they never recover. Another gateway version is that you can actually combine it with a little bit of avocado. So if you already like avocado on toast, you can put a little bit of Vegemite with it, and that just sort of spices it up a little bit. And then, as Steve said, you gradually, as your tolerance levels increase, then you'll find it safe to eat higher concentrations of Vegemite.
Got it. So we understand now the gateway drug into the world of Vegemite. I like it.
Yes, that's right.
I like it. Okay, beautiful.
We have one person at SPEE3D who eats it by the spoonful, and we do worry about him a bit.
I can understand. Well, this has been fabulous. Steve, Andrew, Pierre, I really appreciate you guys being part of this community. Really appreciate what SPEE3D is doing for the organization for CSAT and LSAT. So huge plug to you guys. And obviously you'll be at CSAT, you'll be at LSAT, you'll have presentations at both places. We do have, we're excited to host a similar webinar to this for our friends over at Titomic, another Australian company. There's something going on over there that's magical, clearly. So we'll be excited to talk through what the Titomic team is up to, share a little bit about their work. Again, you can register for the CSAT and LSAT event. CSAT is June 11th and 12th. LSAT is June 13th. We are also accepting abstracts for presentations. So if you'd like to be part of the community that's kind of giving back to the ecosystem, we'd love to have you. Go ahead and check out CSAT and LSAT websites, and they're linked in the chat here at right. And obviously, if you're part of an organization here and you'd like to see yourself in one of these webinars, you'd like to be part of kind of the ecosystem and really help contribute back, we would love to have you. There are plenty of sponsorship options, volunteer options. This is essentially a volunteer-run organization, and so we're really excited to be able to be part of this community, contributing back to the ecosystem. And so again, just want to thank our attendees, thank the team over at Solvus for making this happen. Thank you to the SPEE3D team for sponsoring, supporting the ecosystem, and being such good partners in everything that is making cold spray and large-scale additive happen. So with that, have a wonderful morning, a wonderful evening from around the world. Thank you all, and we'll see you at the next presentation.
Yep, beauty.
Everyone.
Yep, thanks everybody. We'll see you.